So guys, in this video we'll be treating rings. So we'll be checking a very special aspect of algebraic structure, and we'll be dealing with rings. So what is a ring? Now, having idea of what groups are, or and having idea of what algebraic structures are, you need to understand the difference between a ring and a group. So if it is a group has one binary operation, but if it is a ring has two binary operations. So a ring is a non-empty set that has two binary operation called the addition and the multiplication. So all of these binary operation must satisfy all of these listed properties. So the first property that must be satisfied, or the first axiom that must be satisfied before you say that an algebraic structure is a ring, is that the addition must be associative. So addition must be associative. So associativity deals with three different variables. So you can use x, y, z, you can use r, x, and t. You can use any variable as long as they are associative. So the second axiom is that the addition is also commutative. So commutativity means 1 plus 2 is equals to 2 plus 1. That's commutativity. Then we have that the ring must have an identity. So the ring must have an identity element. So an identity element, we can have an additive identity element. We have additive identity element and multiplicative identity element. But in this case, you notice that the identity element in this case is additive. So if you have 1 plus 0, 1 plus 0 is 1, 2 plus 0 is 2, 3 plus 0 is 3. So all of those zeros are referred to as multiplicative identity element. So the next axiom is that every element of R has an inverse. So we must have what we have in this case is also additive inverse. The additive inverse of 2 is minus 2. The additive inverse of 3 is minus 3. The additive inverse of 4 is minus 4. So as you can see clearly that R plus minus R is equals to OR. So when you take the additive inverse, when you add the two additive inverse together, what you have is an identity element. Similarly, just like when you have a variable plus the inverse, you are going to have an identity element. So the next one we have is the multiplication is also associative. So notice that the first one we stated was that addition is associative. Now multiplication must also be associative. So that's axiom number 4. So we have left distributive property and the right distributive property. These are the last two axioms that must be satisfied before you can say that an algebraic structure is a ring. So moving to the next, we have the examples of rings. So we have about 7 examples of rings. So the first one we have is the set of integers. The set of integers is a ring. So the zero element there is 0, and the multiplicative identity is 1. So also rational numbers. The set of rational numbers are numbers that are written in form of fractions such that the denominator is not equal to 0. That's rational numbers. So they are also good examples of rings. Also the set of 2 by 2 matrices with real numbers as entries. This is a good example of rings because they all obey all of the listed earlier axioms. So that is the third one. Then we have even integers. The set of integers, the set of even numbers, they are rings. But in this case there is no identity element because we have negative integers is also included. And recall that the identity element that we have multiplicative identity element. So there is no identity element. So we have continuous function from R to R. Continuous function from R to R is also a typical example of ring. Then we have the set of polynomials. The set of polynomials, anything that is a polynomial, a1x, a2x squared, a3x raised to power 3, a4x raised to power 4, and keep on going like that. All of these are examples of rings. Then finally we have congruence classes in modulus. In modulo, not just in modulus 6, right? We have other ones. So congruence classes in different modulus are typical examples of ring. We have a whole lot of them, but these are the major ones that we'll be reviewing in this video. So the next thing we'll be reviewing is integral domains. Now there is no way you do rings without understanding what we mean by integral domains and zero divisors. Integral domains and zero divisors. So when working in the set of real numbers, you often consider that when you multiply two products together, two variables together, a and b can be zero. If you pick two elements and you multiply them together in the set of R, it's possible that the two of these elements is going to give you zero if one of them is equals to zero. So if I'm picking two elements from the set of integers, and I'm multiplying them together and I'm having zero, it simply means that at least one of these elements must be zero for us to have our answer to be zero. Is either a is equals to zero or b is equals to zero. So now a and b is equals to zero. So is the same true for every ring? Is it true for every ring? Now for example, a ring of matrices, we have ring of 2 by 2 matrices. So you can see that we have two sets. We have matrix A and matrix B, and when we multiply the two of them together, we all have zero. So you can see clearly that the product of two non-zero matrices can also be a zero matrix. So now we want to define what we mean by integral domain, but you can't understand integral domain without understanding what we mean by zero divisor. So what is a zero divisor? Now an element, let R be a ring with zero elements. So we have a ring and the elements in these rings are zero. So we are picking an element A that is inside R. So that element A that is inside R is called a zero divisor if and only if A is not equal to zero. It is a zero divisor, but a zero divisor does not mean that the number is zero. So a zero divisor can be a whole number. It necessarily might not be zero. It can be any other whole number. It can be any other real number, but it can never be zero. So A is not equal to zero such that there exists another element B which is not also equal to zero. So a commutative ring that has an identity element, is called, that contains no zero divisor, is called an integral domain. So an integral domain, we often represent it with the symbol Z. So when you see Z is representing an integral domain. So the ring must be commutative first. So after being commutative, there is no zero divisor. So a commutative ring that does not have a zero divisor is called an integral domain. So this is where we stop in this video. Thank you.